Alright, so let's take an example in this class. Previous class we gave you the different ideas what happens for 2 dimension. So let's take example and proceed. So actual example with numbers, examples. So I'm going to take hx as the same thing, that is the quadratic form is the same, and we'll see that things changes. Alright, so I'll take it as x square plus y square plus 2xy. So which corresponds to looking at xy 1 1 1 1 and xy for me. Is that okay? So the eigenvalues of this matrix, eigenpairs are 2 and 1 1 and 0 and 1 minus. These are the eigenpairs. Fine. I want orthogonal, so I'll write it as 1 upon root 2 of 1 1 and this as 1 upon root 2 of 1 minus 1. Fine. Is that okay? So those are the linear forms that I am looking at. So I am looking at the linear forms as multiply by xy. So I get x plus y upon root 2 and I get x minus y upon root 2 as my linear forms. Alright, these are the linear forms that I am looking at, because I am supposed to look at the transpose of this and then multiply by xy. So if I take the transpose of this, I will get xx, xy, transpose of this will give me x minus y and so on. Fine. So I get this part. So first example, so A, let fxy is equal to x square plus 2xy plus y square minus 8x minus 8y plus 16. I want to look at this. Fine. So this is nice form. You can easily see yourself that it is x square. I have taken care of here, x plus y upon root 2. So what I have written here is that fxy is equal to 0 is same thing as looking at, so look at this x plus y upon root 2 whole square, 2 times this, plus 0 times x minus y upon root 2 whole square, x square plus y square 2xy, this cancels out, you get this part, is equal to 8x plus 8y minus 16. From here also I can take 8 common. So 8 root 2 common, I can write it as x plus y upon root 2 here, fine, minus 16 as it is, just like that. So you can see that this gives me this expression, this is what I have written. Be careful, I get this part. Alright, fine. So just this, so this implies, or is implied by x plus y minus 4 is 0, exactly one line. Fine. So if you remember, we did get exactly one line when alpha 1 was 0. Fine. That case was there with me. Fine. B, I define, so I take fxy as x square plus 2xy plus y square minus 8x minus 8y here. Fine. So this tells me that again I have x plus y, but there is no constant here. Alright. So if you look at this part, here I could divide by 2 and 2 and proceed here. So I could get only complete square here. Here I will not get the complete square. Fine. So look at it nicely. So what I will get here is, it turns out that this is equal to 0 if and only if x plus y minus 8 into x plus y is 0. Fine. So I get a pair of parallel lines. Recall that I had got that set also, parallel lines in the previous class. Go back and have a look at it yourself, you will get that part. And the next idea was that in this I got what is called a parabola. So let me take another C for which I get a parabola. So f of xy, I define it to be equal to, I take it as x square plus 2xy plus y square minus 6x minus 10y minus 3. I take this, all right. And I am looking at f of xy is equal to 0. I have written it as fxy equal to 0 is equivalent to looking at x plus y minus 4 upon root 2 whole square is equal to minus root 2 times x minus y minus 19 by 2 upon root 2. This is what I have written my expression, all right. So, this is what I want you to understand, that in general I will get some constants. If I want to play with this, all right, I am getting here x plus y upon root 2 whole square into 2, fine, minus 6x or minus of 2 times 3 and 5 xy here minus 3 is equal to 0. I am getting this. So, I should be able to write this, all right, in terms of first x plus y and this, that is first thing. The second thing I need to do is that I should be able to get them as x plus y is here, x minus y is here, all right. So, what I am trying to say here is that because of the linear forms, I am able to get x plus y and x minus y. See, the linear form here was x plus y upon root 2 and x minus y upon root 2, all right. So, these were the linear forms. So, one of the expression x plus y is here, another linear form is here that you are looking at. So, therefore, whenever you have such an expression, because of the linear forms, you can decompose it to get orthogonal lines. Is that okay? So, this line and this line are orthogonal. The slope of this line is minus 1, the slope of this line is 1. Is that okay? So, this is just because of the linear forms being linearly independent. That is the first thing, that you can get a solution of such a type. The second thing is orthogonality comes because of the U being an orthogonal matrix, fine. So, just look at it, do yourself, you get things, fine. So, it turns out that this is nothing but the parabola which looks like this. So, I don't know, I wrote some line, so it is not passing through origin. Where does it pass through? I don't know, fine. So, I have something like this, and this is a parabola which goes like this, fine. So, verify yourself, get the things yourself and try it out, fine. So, I have looked at the two dimensional case for you. I want you to understand that. So, this example was only when, so in this case we have taken one of the eigenvalues to be 0. So, one of the eigenvalues to be 0, fine. So, now what are the cases, different cases left out, all right. So, you can look at different cases. So, case 2, so second case will be alpha 1 and alpha 2 are positive. So, I would like you to try that out yourself. So, you can take the matrix A as say 3 1 1 3, fine, or let me make it, let it be 3 itself, so that you get symmetrical, you can understand it easily. Look at different cases. So, construct the examples yourself. So, what I am saying is that you take f of x y as 3x square plus 2xy plus 3y square, fix this part, and in this part keep changing, all right. So, look at this example, this is what I did. In all the three examples, this part is the same, all right, this part is the same, and then I have made changes here to understand the different ideas. Is that okay? So, I want you to do the similar thing, that fix them and look at different examples. Is that okay? So, this is one example that you can look at, where I am saying that alpha 1 and alpha 2 are both positive. Similarly, look at the case when alpha 1 is positive, alpha 2 is negative. You can think of that, fine. So, for example, you can take A as 3 1 1 minus 3, fine. So, here I can see that one of the eigenvalues will be positive, the other will be negative, or I do not know what the expression will be, it may be a bit complicated. So, you can modify it slightly and proceed yourself. So, try that out yourself. Now, I will go to what is called the 3 dimension, all right. Is that okay? So, let me go to 3 dimension for us now. Proceed to R3. Is that okay? So, in R3 I will have got 3 things. F of x y z will be equal to x y z, a matrix A which is 3 by 3. I will have x y z. Again I will have 2 times some f g h x y z plus a constant c which is u. This is what I will get. Is that okay? So, the form will remain the same. Earlier I had the form was, recall the form was x transpose A x plus a vector B transpose x, which is B here, plus C equal to 0. Fine. I also have the same form here itself. In 4 dimension also, or 5 dimension, whatever dimension you want to understand, the expression will be similar in nature. So, for each one of them you are supposed to look at just this part. So, look at this Hermitian form, or the quadratic form, whatever you want to call, quadratic form, Hermitian for over complex, quadratic over real numbers, and so on. So, write x transpose A x as alpha 1 u square plus alpha 2 v square plus alpha 3 z square, where u, v and z are linearly independent linear forms. All right. Do that yourself. Whatever way you want, you can do that. So, what we are saying is that linear forms are independent, means I have got linearly independent vectors. They are orthogonal also. So, linear forms means they come from orthonormal set of vectors. Is that okay? Fine. So, once I have got orthonormal set of vectors, I can replace each x here by u, v and w. Fine. So, I will get something nice here. So, I will now write it as f of u, v, z. Already I have written z. So, no, this z can be confusing. So, let me write w here, u, v, w, as alpha 1 u square plus alpha 2 v square plus alpha 3 w square plus now some 2 times d1, d2, d3 times u, v, w plus a constant c is equal to 0. This is what I will get now. Fine. So, the complicated part, which was x transpose A x, is nicely written like this. Fine. And now I can again do the same thing. I can look at d1 times u is here. So, I can write it as, so if I am assuming that alpha 1, alpha 2, alpha 3 are all non-zero, I can do nice things. If it is 0, I will have issues. So, need to look at different cases, need to look at different cases. What are the cases that we need to look at? One will be that alpha 1 is equal to 0 is equal to alpha 2 and alpha 3 is not 0. Fine. You have to look at this case. You have to look at the case alpha 1 is 0, alpha 2 and alpha 3 are not 0, and the third case none of them is alpha 1, alpha 2, alpha 3 not 0. So, I will have to look at all the 3 cases. In each of the cases again I will have to look at positive, negative and so on. You will have to be careful and proceed. Fine. So, you need to understand each of the cases separately. So, if alpha 1, alpha 2, alpha 3 are positive, then you can get what is called an ellipsoid. Why you will get an ellipsoid? Again understand that nicely. All these are the axis, the length of the axis, in some sense they correspond to that part, and you can look at this here. This expression in this case will turn out to be alpha 1 is outside. You will get u plus d1 upon 2 alpha 1 whole square plus alpha 2 v plus d2 upon 2 alpha 2 whole square, unless I have done a mistake. So, be careful, because I am very good at mistakes. So, you will have to rewrite yourself w plus d3 by 2 alpha 3 whole square is equal to some constant. Fine. So, if this constant is positive, if constant is positive, you get ellipsoid. If constant is 0, fine, you get 3 lines, u plus d1 upon 2 alpha 1 is 0, v plus d2 upon 2 alpha 2 is 0, and third one. So, you get a point of intersection of those lines. Third one, write yourself, d2 plus something is 0, you will get it. If constant is negative, no solution. Fine. Because I will assume that alpha 1, alpha 2, alpha 3 are positive. or you can just say that alpha 1, alpha 2, alpha 3 are of the same sign, and then relate the two ideas directly yourself. All right, fine. You can also from here say that if alpha 1 equal to alpha 2 equal to alpha 3, all three are constant, then you will get an sphere. Fine. So you can change this idea according to circle and ellipse. Similarly, a sphere and ellipsoid that you have. Fine. Now, if here in the third case, so third case, if alpha 1 is positive, alpha 2 and alpha 3 are negative, fine, then I will get it as alpha 1 times u square. I will just keep d also inside, so d times u here, so 2d I think I wrote, I don't know what I wrote, so I think I wrote 2d. So whatever I write 2d1 du, so I can put this alpha 2 out the other side, alpha 2 times v square plus alpha 3 w square, or minus whatever it is, minus d2v minus d3w plus constant here. Fine. Again I can write it as alpha 1 u plus d1 upon 2 alpha 1 whole square is equal to alpha 2 times something plus alpha 3 times something. Fine. So I will get something like this part. Fine. What will this object be? Fine. So you have to again careful. So what you are writing is that you can write like this, but you need to understand that also I can put these alpha 1s inside, alpha 2 inside, alpha 3 inside. I can do it. So in some sense I am going to get an expression like something like x square minus y square minus z square is equal to constant. Fine. Is that okay? So I can assume that constant is positive. I can assume constant is positive. Constant positive. Because if it is negative, negative will imply that I can look at y square plus z square minus x square as constant, which is positive. Is that okay? I just multiply minus 1 throughout. Fine. So they are going to give me what are called, do you remember something? Hyperboloid of one sheet and two sheets. All right. So there is a notion of sheets here that comes into play. I think I have written it in my notes or not. Let me just see. I have written. All right. Fine. So if I take this as positive, this will be hyperboloid of two sheets. Two sheets. This will give me hyperboloid of one sheet. Of one sheet. Fine. So what I am trying to say is that you can just build up your ideas from here. Fine. So positive, negative, I have taken care of all of them here in some sense. This also tells me that two eigenvalues are positive, the other is negative. So that case is also taken care of. My only case now left out in some sense is one of them is 0 and the other two are not 0. Alpha 2 and alpha 3 are not 0. Fine. I also have a case where alpha 1 is 0, alpha 2 is 0, alpha 3 is not 0. You can look at that part also. So alpha 1 0 is equal to alpha 2, alpha 3 not 0. So you can look at that part also. So when alpha 1 is 0, what does it mean? I get something like u is equal to, all right, something like alpha 2 v square plus alpha 3 w square plus d1 v plus d2 w plus constant. All right. So you can see that you are getting in some sense of parabola, because in parabola the equation was y square is equal to 4ax. So there was one square term and there was a linear term here, to a square. This was a linear term. Fine. So I need to understand both of them separately. Further, if I look at these two, if alpha 2 and alpha 3 are positive, that is one case, or alpha 2 alpha 3 is negative. So I should not write alpha 2 alpha 3 positive. Alpha 2 into alpha 3 is positive, accordingly the direction will change. So there are two cases, this is positive, the other is negative. This will give me hyperboloid of a different type. So this is called parabolic hyperboloid, parabolic hyperboloid. This will give me paraboloid itself. and this is positive, basically means that I have got some sort of ellipse. So, at each place if I put u to be something, fix a constant for this u, I will get this. So, in this case I will get an expression. So, the figure will be something like this that I will be looking at. So, this is the parabola I am looking at, that each of these are nothing but these are ellipse, because alpha 2 and alpha 3 are positive. So, I will get an ellipse here, fine. If u is negative, these are some high numbers, this part will become 0. So, I am going to get only one part. Is that okay? This basically means that each of the intersection, each of the, say what should I say, the cutoff that you look at, all right, if you cut it something, then alpha 2 is positive, alpha 3 is negative, or vice versa, will give you, each of them should be hyperbola, all right. So, if I look at this cutting here by a plane, I am getting a circle here, all right, an ellipse in some sense, all right. What I want here is, now in this case, all the intersection that I am going to look at with the plane, that is this u equal to 0, is going to give me hyperbola, and therefore I got a hyperbola. Is that okay? So, I find it difficult to plot these graphs. All right, so this is the example which I wanted you to see here, that what happens in case of 3 dimension. So, I have got some of the figures for you. So, this corresponds to, this figure corresponds to looking at A as this matrix 2. So, the matrix is 2 1 1 1 2 1 1 1 2, which corresponds to, so eigenvalues are 4, eigenvector is 1 1 1. So, this will give me 1 upon root 3 times this as my unit vector. I have an eigenvalue which is 1, which corresponds to 1 upon root 2 minus 1 upon root 2 0 as an eigenvector. Fine. So, this is an eigenpair, this is another eigenpair, and the third eigenpair is again 1, but here it is 1 upon root 6, 1 upon root 6 minus 2 upon root 6. All right. So, this is the eigenpair that I am looking at. So, my orthogonal vectors are these 3 orthogonal vectors, and therefore, I get this, if you can see here, that this is the ellipsoid that I have got, ellipsoid, as alpha 1 is 4, one eigenvalue is 4, the other eigenvalue are the same. So, I get an ellipsoid. Is that okay? So, all 3 are positive, and I have got this for you. Is that okay? So, this gives me the ellipsoid, and these are the 3, look at here, these are the 3 which are orthogonal, all right, fine, principal axis that you are looking at, and that is what the requirement was, fine. Look at the next one. The next one is, this is the parabolic hyperboloid, So, you can see that if I cut anywhere, so if I want to cut like this here from here, I will get something like this, fine. So, I am going to get here, and again something here I am going to get like this. Is that okay? So, each of these sheets are separate in some sense, fine. If I just cut it, I will get 2 parts and things like that. So, I would like you to see this nicely, and the equation of this is, I have written as z is equal to y square minus 3x square plus 10. This is the one that I am looking at, fine. So, depending on z is positive or negative, you can keep changing here, and you can keep getting it here, fine. So, this was parabolic hyperboloid. The other one I forgot to write, I think you could have taken here as y square plus x square plus 10. If I take, I will get z is increasing with this height. So, as z increases, these things, the size of these things will also increase, fine. Just look at it. If z is increasing, yx square, the value of x square can also increase. So, I will get, and if I take z as to be minus 10, z is equal to minus 10, I will get x square, or z as 10, sorry, z as 10, then x square plus y square is 0. So, x and y will be 0. So, at this point, at z is equal to 10, it will start and it will go like this, fine, and each of them will be an ellipse that will come into play. Is that okay? The next is, this is the hyperboloid of 2 sheets, and the equation that I have written here is, hyperboloid of 2 sheet is 3x square minus y square plus z square plus 10 is 0. So, what you are writing here is, just see here 2 sheets, basically because plus 10 I have to put it that side. So, I will get negative, fine. So, what I will get is y square minus 3y square minus z square is 10. This is what I had written. I had taken everything with respect to this being positive. All right. So, this is positive, there are two of them. So, there is a two sheets, one sheet here and one sheet here. There are two sheets, fine. And the last one is hyperbola of one sheet. So, let me add that equation. So, hyperboloid of one sheet. Here the equation is 3x square minus y square plus z square is 10, the same thing that I wrote, fine. So, this is again I have taken at positive, and there is only one negative, all right, only one negative implies one sheet, all right. In the previous one, if you see, I had two negatives here, and therefore there were two sheets. Is that okay? So, they get related with these ideas that you have. So, these are the four diagrams that I have for you. One is ellipsoid. So, one was ellipsoid, the other is parabolic hyperboloid. For the main paraboloid, where each of these things are ellipse that I have not plotted, but I have given you this equation here that you can check for yourself. This is two sheets because they are two separate parts, and there are two negatives when I write the constant as positive. So, constants have to be always written positive so that you can make statements. And the last one is this, only one sheet here, and this is the one that we generally have, what is called a modha at our place, at our home. It's sold in the market. You have these modhas that you have in this size. So, these are the modhas that you are looking at, fine. So, that's all for this course as far as geometry is concerned. As the last lecture, I will talk about, all right, what is called the singular value decomposition, which is not in the syllabus as such, but I will just give you some brief idea about it so that you can use it in your applications. That's all.